Last paper presentation is from Gleison Roberto de Nascimento from Campinas University of Campinas, with the paper Solar Energy Forecasting Case Study of the UNICAMP Gymnasium. Okay, so.
Thank you, Professor João. Hi, everyone. My name is Gleison, and I'm here to present this work in collaboration with Professor Hildo Goulart Jr. and Professor Holmes at Tux. Thank you, Professor. What's our general motivation from this work? UNICAMP deals with the national interconnected system. And in this system, UNICAMP contracts about 6,000 megawatt hours each month, resulting in 2,000 tons of CO2 in emissions. This is equivalent to daily emission of 7,050 rendered diesel buses from the Campinas bus fleet. In this case, is urgent in changing to renewable energy sources for now. In this context, we took the oldest and most robust plant at UNICAMP, which the Multidisciplinary Gymnasium, here referred to GMU-PV. In this way, we analyze the data set generated by the inverters of this plant and verify if it is possible to contribute to UNICAMP's energy transition through this data, and also optimize the process related to new plants or the potential to make better decisions with the models developed from this data. All right? These are the most cited and prior works that use artificial intelligence in solar energy forecasting, and that contributed to the realization of this work. So, from the moment we decided to use GMU-PV data and rely on previous works, we then had two research questions to answer. The first was whether it's possible to create a forecasting model with the GMU-PV data. The second was whether this model is capable of optimizing energy contracts and the energy transition at the university, reducing the environment impact. In these processes, we use the CRISP-DM methodology. CRISP-DM is a classical methodology for data science. It constitutes in business understand, data preparation, modeling, evaluation, and deployment. In this case, in this work, deployment is in fundament now, all right? And results from deployment is now showing in this presentation, all right? About our data set. The data set is constituted by a time series from May 4, 2029 to April 15, 2023, and 1443 observations diary, all right? 27 features, electrical parameters from inverters, and solar irradiance and UV parameters, atmospheric and weather conditions from NASA satellites, all right? Our target is the energy produced in kilowatt-hour, all right? Our data set is split in 50% in train, 20% in validation, and 30% in test. Still speaking of the target, the left side, we have statistics indicating that this data do not have behavior in Gaussian matter. In KDE plot and Kiki plot, normal Kiki plot, represents not a Gaussian manner. In box plot, we have a case of sorry about that. A case in Brazil. In Brazil, the system is shut down about 15.9 or 49 below. System shut down, all right? And this is important for our plants. In the right side is energy decomposition, all right, in trendy, seasonal, and residual. Sorry. In this case, is classified as difference stationary, all right? In modeling, this project used three distinct approaches. The first was the univariate time series. The second was the multivariate time series. In both cases, these were non-convergent approaches. The third approach was regression, and in this case, resulted in convergence. The tested regression models with good results tested were OMP, orthogonal matching pursuit, CNN, LSTM, transformer, conformal regression, and profit. From univariate time series approach and multivariate time series approach, we used two reference for regression, 3 and 4 references, all right? The table of numeric results. We used in evaluation EI.A, MSE, RMSE, MAPE, and R squared, all right? All models is adequate, as a good results, but OMP is a Rayleigh model, all right? R2, 93% is a good way, all right? This is the graphical result. And consider the real data and all these models when a good result is quite similar. It's very good performance, all right? So the best model in this case, Rhyolite, is orthogonal matching pursuit. A really not common approach in this case. Machine learning models, the last one you remember is the orthogonal match pursuit. But it's curious, it's the best model in this case. The best hyperparameters from this model is case in he produced this work, all right? Also, the OMP algorithm is a kind of a big solution and a big problem in same time, all right? Because he don't catch the global best solution. He's take the local best solution. This a kind of problem because it's comportamentally is a grid algorithm, all right? But in this case, was a better solution in comparison of the other models, all right? Finally, we conclude that our two research questions could be answered in such a way that the developed model achieved an R-squared a little over 93%, being quite interesting in forecasting process. And it helped to model better opportunities for energy contracting, considering seasonal cycle found in the data. Moreover, an important issue is that all models were subjected to methodologies to avoid overfitting and underfitting, a concern for the size of the dataset. And generally, the difference between the best and the worst models found was a 5%. All right. Okay, this is all authors. And thank you for the patience. And thank you for all of you. All right.
Thank you for your presentation. Is there any question from the audience? You want?
Thank you for a nice presentation. I had a question with respect to the accuracy of the forecast. Was there any difference between winter and summer? I mean, do your model performs best during the summer or the winter, or it's the same?
It's the same. Sorry. It's the same. No, we in this case, graphically, we can see a period, and we have winter and summer in the same way. All right. Graphically, a great big period. Sorry about my bad English. Thank you.
Thank you. Is there any more question? Just maybe a final question. Are you saving money with this forecasting algorithm because the case study was UNICAMP Gymnasium? Are you saving money with
Yeah.
Now,
this is a really
do you
important.
estimate?
Yes. These are a really important thing. These contracts can save about 15 to 20%. In actually, we contract fixed value. This is really bad for us when the weather is variational, the production is variational. In this case, we can play the new contracts considering the periodicity of this. In this case, this project can save about 15 and 20%
Of energy contract.
Contract.
You
Yes.
can anticipate better. Yes. All right.
In public tax, what is really better.
Yeah, that's nice. You are concerned with public money. That's good. And there is another question here, I think. Final one.
Thank you for the talk. The question from my side, it looks like the models all overestimate in the time horizon you have there. Do you also investigate it if there's a bias in your models regarding the overestimation?
The data set have 4 years. This is a little representation, the test representation, but all models are represented in all time. All right, this is test time. Okay, but all models in all time for 4 years. Sorry about my bad English, man.